Okay, ladies and gentlemen, thank you for joining me and Fred at ascendoreliability.com. And today's webinar is all about PDFs, CDFs, and other Fs. What the hell are they? And the reason this webinar, well, the reason why we're focusing on this topic is a lot of the time, many of us think we know what these probability, what these functions are, what these names mean, what these acronyms mean. But often we just don't have the time to really reinforce their true meanings, and especially if you're a manager or your manager's not on top of some of these concepts. Going back to basics and really understanding what these functions mean and what they do can be really helpful, even if we think we're on top of reliability engineering topics more broadly. So what we're going to talk about today is the very first principles approach, and hopefully a very basic and illuminating first principles approach to understanding what each function means and what it means for us as reliability engineers, particularly when things fail. So before we go into too much detail, we're going to start at the very start, and that means looking at a line, which in this case represents, say, some sort of magnitude, some sort of random variable we want to learn about, something we're investigating, something that matters to us. And in the line of reliability engineering, often this means things like time to failure. Now, when something fails, it goes through a random process. Failure is a random process. Transistors have different diffusion speeds. Operators use our products in different ways, and there are different build qualities, so on and so forth. So when we have a number of products fail, there's going to be some inherent variability, and each one of these dots or circles represents a single failure point. We can see that there is a certain amount of variability with our random variable, which is time to failure. But we can also see that values are more likely to occur in this region. Now, I'd also ask that while we're going through this very basic stuff, if you have any questions, please ask the questions through the Padlet or through the chat window. We'll do our best for those questions to get to me, and we'll answer them as we go, because it's very important to understand some of these underlying topics. So here is our random variable, and in this case, we've got a bunch of these random variables. They're all the same thing. They're the time to failure for a particular product or a system. Now, we can see that they tend to occur in a certain region, but that's often not a really easy thing to visually represent. A thing that we are more comfortable with in terms of representing the nature of failure is this sort of thing here, a histogram. And then you can see that these bars sort of give us a rough indication of how often or how frequently our random variable is occurring in a certain region or space. But to be fair, this is a very ugly chart or ugly graph. You can see it's not smooth. You can see that it looks like a very toothy grin. Some columns are higher than others, where you'd expect a more smooth result. So what can we do about this? What does this mean for us as people who are trying to understand the random nature of a process, in this case failure? Well, you might recall from my previous webinar on probability plotting, what we can do is we can order these points from, in this case, from 1 to 100. We want to have 100 data points here. And instead of looking at it as a histogram, we can essentially create this chart here where the vertical axis is the percentage of events that have already occurred. So what this means is that as we move from the left-hand side to the right-hand side of our chart, we would expect, we see the vertical position of our points going up as it approaches 100%, because as we move further to the right, we are essentially passing more and more of our data points until we passed all of them, or 100%. And this creates potentially this nice little curve here, which is shaded in orange. But if we move on to the next iteration of what this actually means, we can potentially manipulate these charts, manipulate these axes, and have these weird scales here to create perhaps a straight line. And if the data follows a straight line, then we can say something about what the underlying probability nature is. Underlying nature of probability is, the nature of failure, how things are failing, what is causing, or sorry, the characteristics of the random process of our system no longer working. Now, if we say this is a straight line, then we can make some conclusions, but I'm not going to go down this any further, because if you want to understand how we can interpret data and create or infer what a likely probability distribution is that explains our random process, please look at our probability plotting webinar to learn more. So let's assume that you have gone through some sort of process to understand or characterize the random nature of our random variable. And this allows you to create, for example, this shape here. And we'll go into what this shape means in the near future. But this shape is an outcome of a description. It's a framework which describes the probability, the nature of probability, the likelihood of our failures occurring at a certain point in time or a certain point of usage. And you can see it has sort of a much smoother curve. And in this case, this is a Weibull this is from a Weibull distribution with a shape parameter of 5.28. Again, go to our probability plotting webinar if you'd like to learn more about how we get this shape. But you can see it is a lot smoother. And hopefully visually, you can understand what it's trying to summarize. It is trying to tell us that there is a region of higher likelihood or higher probability of occurrence of failure when compared to other regions. And it has sort of this, almost bell-like shape. So even though this is a random process, we can still perhaps go through some data analysis process to create a shape like this, which means we think we can characterize the uncertainty. And I haven't seen any questions come through yet. It might be a technical glitch, but if there are any questions, please please do not be shy in putting them into the chat window or into the Padlet. So going back to our curve, this lovely smooth hill, you can see that it entails information. And the most important takeaway from this chart is random doesn't mean unpredictable. So we are interested in understanding the random nature of things. But when we say random, so often our first inclination is to think there is no rhyme or reason to what is occurring, and that's not true. If we can understand the random process, we can then make really meaningful deductions, which help our business. So let's go back to this curve here. How can we use this curve to, for example, tell us when our warranty period should be if we want to make sure that no more than 5% or 1 in 20 of our products fail in the warranty period? This is a very common question that manufacturers ask. What about if this is a key part of a system or a plant, and we want to know how many of these things we expect to fail in 1 year if we just simply run it to failure? Maybe it's a pump, maybe it's a valve, and for whatever reason we're happy with it running to failure. So but we do want to know how many we expect to see fail every year. Well, what if your question revolves around, hey, I don't want it to fail, I don't want it to run to failure. When do I need to service it, or when do I need to swap it out? When do I need to overhaul it so that no more than 1% of my things fail before my next overhaul, my next replacement, my next lubrication, so on and so forth? Or perhaps an even more important question, is servicing even a thing for this product? Well, our probability curve that we just looked at can tell us what the answers are to all of these things. We just need to know how to interpret it and how to look for these answers. So here it is here. Here are the questions where we want to ask about our product, and we've gone through some data analysis process to get this curve here, which describes the nature of our failure process, which is inherently random. And so let's take away all the noise, let's take away all the data points, let's take away all the histograms, and we're just left with this curve here, which summarizes the relative likelihood of failure. We call this curve the probability density function, or the PDF, which gives the relative probability that a continuous random variable is equal to a specific value. And the higher the value, the more likely that the random variable is going to, so more likely it is so that random variable will occur at that point. So let's look at an example PDF. you can see we have the horizontal axis, our random variable, which in this case is t, and this curve here summarizes the random nature of whatever process defines our random variable. And you can see here that if we look at this curve, it seems to me that most values, most random variable values are going to occur around 2. It seems to be the highest, the point where the PDF curve has the highest value. We can also see that this curve doesn't extend below 0, so there's no chance of this random variable having a negative value. But there's also another characteristic of this PDF curve, and our PDF curve must be a curve where the area under it is equal to 1. Why is that? Because we need to use this property to answer all the questions we just asked ourselves, and I'll show you why. So for example, let's just say we want to understand what the probability of our random variable having a value between 2 and 6 is. Well, this area under our curve, which is the area within the interval 2 to 6, will tell us what that probability is. Now, the reason why the area under the entire curve has to be 1 is because essentially that means there is a 100% chance of our random variable having some value. So any area under the curve which is based within a specific interval represents a smaller value than our 100% total. It might be 50%, might be 60%, but this area can then give us meaningful answers for questions like, what is the probability that our random variable value will be somewhere between 2 and 6? And another key observation from this little property is that our probability density function curve has no direct meaning. What does that mean? Well, we go back to our PDF here and we got this interval which shows that the probability of our variable being between 2 and 6. Well, let's look at what happens when we collapse that interval. Instead of wanting to know what the probability of our random variable being between 2 and 6 is, what does it look like if it's between 2 and 5? What about 2 and 4? What about 2 and 3? What happens if it collapses all the way to 2, which should tell us the probability that our random variable has a value which is exactly or precisely 2? Well, the area under the curve here is 0 because it's bounded on the left by 2, it's bounded on the right by 2. So because this is a continuous random variable, we can't ever say that there is a finite probability of our random variable having any specific value. So the height of the curve is somewhat meaningless. The probability that a continuous random variable can take on a specific value is 0. We must deal with instead intervals. Now, intervals are problematic, and we're about to show you why. Because intervals mean we need to worry about the area, and the area itself can be difficult to calculate. So what we can do is create another curve which helps us answer questions based on the area. And as you see here in this little animation, as we move from left to right, as we start from 0 and move up to 6, the curve on the bottom gives us the area under the curve on the top. And we'll just go through that one again. If you missed it the first time, you'll see that as we move from the left to the right, starting at 0, the area under our PDF curve increases, and the curve at the bottom tells us how the magnitude of that area as we move from left to right until we get to, in this case, a value of 6. So if we want to understand the probability that our random variable occurs before 6, we simply take that height of the bottom curve, which in this case is 0.9693, which tells us that there is a 96.93% chance that our random variable occurs before 6. Now, if our random variable is time to failure, this means there is a 96.93% chance that our system fails before 6 hours. Now, this is how we interpret the PDF curve in a way that gives us meaningful statistics. Now, I can see that there's an audience question coming up. Can Minitab give those values neatly and easily? The answer is obviously yes, as I think, Fred, that was your response. once you know what the PDF is, you can generate all the answers, all the curves we're about to go through really easily. The trick here is understanding what the right PDF curve is. And again, that's almost the subject of another lesson where you're trying to work out if you've got data, for example, how you match a given probability distribution to that data to answer questions like this. And the next question is, what is the difference between probability and likelihood in a PDF? I hear likelihood a lot in the context of PDF, so that's a really good question. So for example, there's a branch of analysis out there which relies on what we call maximum likelihood estimates. Now, when we typically look, likelihood and probability are technically synonymous. The problem is that when we're talking about a probability density function, we are talking about the likelihood of a random variable occurring. What we typically talk about when it's likelihood is we're talking about the probability that an underlying parameter is true. So for example, if I've observed evidence where I take 5 products and 2 of them have failed. So I've got a batch, I sample 5 of them, 2 of them are terrible, 5 are functional. I can use some statistics in the concept of likelihood to work out what the likelihood of the underlying parameter is, which is in this case is the reliability of each product, the probability that each product is functional or not. Now, in statistics, there's a slight difference between the two. We typically, and to make that distinction clear, we often use the term probability to describe the frequency or occurrence or likelihood of us observing the output of a random process, which might be the number of failed products in a random sample of 5. And we often use the term likelihood to explain the probability of a particular parameter for that random process being true, which would be the on-demand reliability. So that's where the difference lies. And there's a couple of other statistical anomalies which make those two terms different. But as a rule of thumb, probability and probability density describes the likelihood of seeing an outcome of a random process, whereas likelihood describes our, I suppose, confidence that a particular parameter value is a certain parameter is a certain value. I hope that helps, and obviously if it doesn't help to the extent it needs to, please send a follow-on question. Okay, so here we have our 2 curves. The top curve is our PDF curve. The bottom curve gives us the area under that curve up until 6. But let's just say, you might remember we looked at the area under a curve a couple of slides ago between the values of 2 and 6. How do we find the probability that a random variable lies between 2 and 6? Well, what we can do is collapse the interval again, which means that our little shaded area on the left-hand side moves across, and the corresponding value on our area curve at the bottom also goes up. Now you see that at 2, our area curve at the bottom has a value of 0.3824. At 6, that value is 0.9693. So the difference between those 2 values gives us the probability that a random variable is between those 2 boundaries of our interval. So the probability that our random variable is between 2 and 6 is somewhat difficult to evaluate directly when we look at a PDF. But if we have a CDF or our area curve in the bottom, got ahead of myself in terms of naming that curve, we can relatively easily work out what the area values are at the extremes of our intervals, take the difference, and that answers our question. So the PDF curve gives the slope of the area curve, and the area curve gives the area under the PDF curve. So whenever you have a PDF curve, you obviously have also defined the area curve at the same time. You need some mathematical trickery to get from one to the other. But for every PDF curve, you obviously have a corresponding area curve. Now, this area curve tells us the probability that the random variable value is less than the value on the horizontal axis. Or in reliability engineering, the probability that our product or system has failed. And as you can see, this curve keeps going up until it approaches 1, because eventually everything fails. So obviously this curve must keep going up, keep going up, keep going up, approaching but never quite equaling 1. We call this curve our cumulative distribution function, or the function that gives the curve the cumulative distribution function, because it gives a probability that a random variable is less than or equal to a specific value. So we have covered so far the PDF curve and the CDF curve for a random variable. So how does this help us? Well, let's go back to our random variable. In this case, time to failure, we have a bunch of data in this case, or this is some sort of test or field data, what have you. We know that we can, or visually we can see that values are more likely to occur in that region there. If we put a histogram up, we can see that the histogram supports that idea that the values are more likely to occur in that sort of region where all those data points double up, but it's still quite a uneven trend in the heights of those histogram columns. But if we plot this on those axes we looked at previously, knowing what we now know, the vertical axis becomes the estimate of a cumulative distribution function. And you can see that straight away, the line is a lot smoother. The histogram was all jagged, but as soon as we move from the PDF space in terms of raw data into the CDF space, our data becomes a lot smoother, which is always a thing we need to exploit when we're doing data analysis. And so from our data analysis, from our probability plotting webinar, we can use this data to get an estimate of the true underlying cumulative distribution function, which is this curve here. And this is what, if we assume a Weibull probability distribution, this is the curve that data analysis gives us. This is our CDF curve that some data analysis has spat out at the other end. So let's see how we use this curve. Now, remember those questions we asked at the start. I might be interested in understanding the warranty period of my product. So if I define the warranty period as a period in time where I want no more than 5% of my product to have failed, when we go on the vertical axis here, find where 5% is, go straight across to our cumulative distribution function, and this is our warranty period. So our CDF can tell us when we should have a warranty period if we know roughly how many things we can tolerate failing in that warranty period. And you obviously should know that if your finance team should be able to understand the likely cost of warranty action, and obviously work out how many you can tolerate before you start eating into your profits. So this is our warranty period. Perhaps we're interested in making sure we're an asset management framework. We want to make sure that we have, when we actually can't tolerate 5% of failure, warranty is not a thing. We want to swap out our part, our component, our pump, our valve before it likely fails. And let's just say we can tolerate 1% of our valves or pumps failing before we do conduct our preventive maintenance or servicing action. Then we find, well, that 1% is what we can tolerate, 1% on the vertical axis, put that across to our CDF curve, and this means that we now have what could be our servicing interval. So once you go through the process of taking your data, understanding how to create a PDF and a CDF, and you get your CDF, you can answer really useful questions like this. When should my warranty period be? How often should I service it? So the question I would ask to the audience here is, those involved in warranty periods or servicing of plant, has this approach permeated your thinking, your thought process, or is it something that do you guys, is there a prevalence of, let's just say, MTBF, MTTF dominating analyses like this? Does the MTBF or MTTF tend to dominate, at least in your experience, questions like when should I service and what our warranty period should be? So I'll just leave that hanging for a little bit and see if I can get the questions coming through. I guess, Fred, you're retweeting them as they do come through. Just give another couple of minutes. I appreciate that not everyone might be involved in the scenario where you have to concern yourself with warranty periods or servicing intervals. Okay, no worries. So I haven't seen too many questions come through. All right, so we'll move on. So let's just say you are in an industry where you're worried about servicing intervals or warranty periods or things like that. You might remember the other question we asked, which was all about something else, about total number of failures we expect to see. So let's just zoom back out of our cumulative distribution function. We'll even put our data points back on. We'll even change our perspective from the CDF back to the PDF. But I've kept or highlighted the 2 points we just looked at, which was the point at which where we want to have a warranty period where we expect no more than 5% of our things to have failed, or a servicing interval where we expect to have no more than 1% of our things have failed. And you can see that when you compare it to our PDF curve, it's very much, it's on the left-hand side, it's at the left-hand tail. Now, a question that's just come through is what sample is required for us to have a meaningful PDF and CDF? And that is, as Fred said, is a very good question. Now, I'm going to not answer that completely here because that was a topic of a previous webinar we did, probability plotting. And the short answer is there is no binary answer. With reliability engineering, we need to deal with confidence bounds. So everything we're talking about here, our PDF and CDF, we're talking as if we know exactly what it is. And that's okay for this conceptual discussion. But in practice, we need to not only worry about what we think the CDF curve is or the PDF curve is, we need to concern ourselves with what the PDF curve or CDF curve is likely to be in a very conservative sense. So the approach that we talk about here doesn't change one bit, but instead of using our best guess for our CDF or PDF curve, we do the same process with our conservative estimate of the CDF curve, or what we call the upper confidence bound if it's about failure, or lower confidence bound if it's about reliability. And then you get your own similar curve, but it's essentially the curve which represents your risk profile, the extent to which you're happy that you are wrong, for lack of a better term. Now, in terms of how to estimate the confidence in the PDF and CDF, again, I can't cover it in this lesson. It might be, I'd actually ask people to have a look at the webinar regarding probability plotting. And if you think that doesn't cover it enough, because we do talk about it at the end in regards to software confidence bounds, can you please let us know? And maybe that's a topic for another webinar. Another question is, so warranty goal is better present as max X% of failures by time T. Is that right? So I sense you're borrowing terminology from mill handbooks as it relates to maintainability, and it's not a bad concept. That the percentage time by which you expect 95% of your maintenance actions to have been completed. Yes, the max X% of failures by time T is in this case was 5%. If that met our business goals, then yes, what you're saying is exactly true. The max 5% time where you define that metric as the time by which you expect no more than 5% of your failures to have occurred. And again, you can put confidence bounds on that. Now, another question is interesting point on the service interval as determined by life data. This could be used to validate manufacturer recommended service intervals versus actual life determined service intervals. I would imagine manufacturer intervals are conservative. I'm not going to answer that question right now. I will later on with a slide. So just hold that thought. Now, that next question is, if you know the distribution type, it helps. If you don't even know that, with little points, it is very hard to predict. And I agree with that. Again, I'll ask you to have a look at our probability plotting lesson as well. That helps you choose the right distribution. But I will say that if you just do a little bit of investigation, you can learn a lot about what the typical probability distributions are going to be for your type of failure. So for example, if you're concerned about rubber wearing out on a tire or similar problem, we are pretty comfortable for a number of good reasons that the normal distribution, that the prototypical bell curve, is a great way of describing the variability of how quickly it takes for rubber or synthetic materials to wear away. We also know the log normal distribution is really good for things like fatigue, because the log normal distribution describes multiplicative processes. So as our fatigue cracks grow, the stress concentration increases. So as the crack gets bigger, the rate at which it grows gets bigger as well. So the log normal distribution is really, really good. So I take your point. If you don't have many data points, it is a struggle to work out what the right curve is. But you can do a little bit more investigation regarding the dominant failure mechanism to at least point in the right direction. Now, the audience question, as you can see, the CDF is not 100% fit of the actual data. That means there is certain uncertainty to the warranty that is calculated to 5%. How do you broadcast this uncertainty here? And you're 100% right. This is the topic for a different lecture. And I think because the number of questions being asked about this, Fred, we might have to dedicate a specific lesson to confidence intervals. Again, I can see Fred's put the link to the one on probability plotting where we talk about going through data analysis and putting confidence bounds on our curves at the end. And I would ask those of you who are genuinely interested to have a look at that webinar, that recorded webinar. If there's something you'd like us to explore further or dedicate an entire webinar to, please let us know, and it will be in the works very, very quickly. So let's go back to our presentation, as I see I have exhausted all the questions so far. So just describing the image you can see on the screen. We have the PDF that we have gone through some sort of process to fit to our data the way one of you have suggested. You can see on the left-hand side the point estimates of where our servicing interval should be and our warranty period should be, depending on the industry, depending on what it is you're interested in finding out. So what's next? Well, let's have a look at what this means with respect to the mean. So on the screen now, you can see where the mean is. The mean of this random variable, and we can use the probability density function to calculate this. And we'll talk about what the mean actually, how we get there in a minute. But the point I'm trying to make here is that you can see that our warranty period, our servicing interval, is a lot shorter than our mean time to failure. What happens if we simply make the servicing interval equal to our mean time to failure? Well, we go back to our PDF, and our PDF curve will answer that question for us. We know that the area under the PDF curve between an interval gives us the probability of failure. So if I just focus on our MTTF, this area here, which equates to 48% of the possible random variable values, that gives us a probability that our thing will fail before the mean time to failure. So never ever equate the mean time to failure with things like warranty reliability and servicing intervals. So what is this mean? Well, in short, there is a mathematical equation we can put up on the screen, but I'm not going to do that. I know you probably hate me enough going through all this nonsense. I'm not going to try and lose any more friends than I've already lost. So here's our example probability density function. Now, if we take our PDF curve and we turn it into a shape and it sits in the air, let's now actually give this shape some mass, as in it actually becomes a three-dimensional shape. And if I can balance this mass on this point here, then this becomes our mean. Not becomes our mean, this tells us where the mean is. So the mean is the point at which, if our PDF curve, if it was a shape, would balance perfectly. Now you can see it's not right in the middle. What does the middle mean? Well, some people, they think the middle is a point where the random variable value is most likely to occur. So if we go to our PDF curve and find the highest value, this becomes what we call a mode. So the mode is the value at which that is most likely to occur. The mean is a value where essentially on the balance of probabilities, quite literally, you could balance your PDF such that it wouldn't fall one way or the other. And there's another way we can also work out sort of the typical value, and that is we split it in two. So if we cut our PDF curve into, so there's 50% on one side and 50% on the other, this becomes what we call the median. And so these are three common measures of central tendency. What does that mean? We often want to know some typical indicative value which describes the likely values of our random variable. We want to know what the average height of human beings are. We want to know what the average cost of a certain thing in a shop is, so on and so forth. And so we often can deal with these measures of central tendency, and each have their strength and each have their weaknesses. In real estate, we often use the median because that tends to limit the extent to which a very expensive multi-million-dollar house in a single suburb or subdivision drives up that measure of central tendency. If the median doesn't sort of automatically tip one way or another, if the most expensive house becomes twice as expensive. So we often use that measure in real estate because we don't want one house turning into a $20 million mansion to artificially skew the perceived values of all the other houses. So this is why we have a different number of measures of central tendency, and they all have their own strengths and weaknesses. And technically, these are all forms of the average. The mean is what we often refer to as the average, though. But the mean time to failure in this case helps us understand how many failures we expect to see in a year. Now, I see an audience question about the median. I just see the word median. I hope that's reaffirming what we're talking about in this particular context. But if there's a typo there, or if there's a more detailed question coming, please let me know. But if we're interested in understanding, if we have 10 valves in a plant and they have a 3-month mean time to failure, then we would expect, if we're going to run each valve to failure, we'd expect the valve would have to be replaced on average 4 times a year. The mean time to failure, or mean time between failure, is 3 months. If we have 10 of them, and we expect that we go through 40 valves in 1 year. So the mean helps us understand things like how many parts we need to maintain our plant. But that is not a reliability engineering question. That is a logistics engineering question. If we're in the business of reliability, we want to know things that can help us improve the performance of our product, and MTBF and MTTF can't. So what is left? What haven't we talked about? We talked about the PDF curve, we talked about the CDF curve, and we talked about some measures of the central tendency, and hopefully that visual with the PDF curve helped you understand what those measures of central tendency are. So what else is left? Well, if we go back to our PDF curve here, and we know that the area under that curve gives us what we call the cumulative distribution function, the CDF. And so as soon as we have one curve, we can automatically define the other. Then if we just focus on the CDF itself, we can plot this other curve here, which is simply 1 minus the CDF. Because it's 1 minus the CDF, it's obviously the same shape, it's just upside down. The CDF curve starts at 0, which makes sense. None of your products should have failed, dead on arrival, systems or products aside. None of your products should have failed at time 0. And as you keep using your product, using your device, using your system, the probability of failure increases. Well, if you flip that on its upside down, we could say that the probability that our system or product is working at time 0 should also be 1. So instead of looking at the probability of failure, we're looking at the probability of success or function, which means this red line here becomes our reliability function. And to be honest, we're not going to be spending too much more time on that, what the reliability function is in a statistical and mathematically derived sense. Why? Because it is so similar conceptually and philosophically to the CDF that if you know how to get the CDF from the PDF curve, then essentially you know what the reliability curve is also. Where the CDF curve gives you the area under your PDF. If you look at it to the left-hand side of that point in question, the reliability curve looks at the area on the other side. One is all about the probability of failure. The other one is all about the probability of success. The other question is seen coming up is, does the area under a CDF curve tell us anything? Which is a really, really good question. From the direct answer is no. The area under the CDF curve does not tell us anything meaningful. The area under the reliability curve can be used to help calculate what the mean value is from a very mathematical sense. You can use that area to calculate where that balance point is, where your PDF curve would perfectly balance on top of it. But in a very direct sense, does it have an actual probabilistic meaning or physical meaning? No. In fact, the area under the CDF curve, if you extend it all the way to infinity, will be also infinite, because as it approaches 1, you essentially have a curve which is at 1 as far as you can possibly go. So it's a really good question. It's the area under the reliability curve we are sometimes interested in if we want to calculate the MTBF or MTBF. Excuse me. Right, so that means we've covered the PDF, the CDF, the reliability curve, and some measures of central tendency, the mean, the median, and mode. Is there anything else? Well, there is one more thing we need to concern ourselves with. So here's our probability density function curve, and here is our reliability function curve as well. Now, just in the same way that every PDF curve defines a CDF curve, every PDF curve must also define a reliability curve. So if you have one, you can automatically define the other. Now, if we divide one by the other, we can get what we call a hazard rate, the rate at which a functioning system fails with respect to usage. We use the Greek letter lambda to give us this, this value. So lambda is equal to our PDF value divided by our reliability value. And the reason we're interested in this curve, this blue line here, is because this tells us the instantaneous likelihood that a system or product that is currently working will fail now. So I'd ask this question broadly. We can see this blue line starting at 0, and it seems to be increasing all the way up to the right-hand side. What does that tell us about the nature of failure for this particular product? Can we learn anything about it? I'll just leave that question out there, see if we get any responses. So we've lost audio. It's not good. I've just turned on subtitles at this stage. Hopefully you can recognize my accent, and you can see the words coming at the bottom of the screen. So we had one response. We had that this has an increasing failure rate, increasing hazard rate, which is absolutely correct. Which typically, well, not typically, which means that our system is wearing out. So you remember the question, one of the questions we asked at the start of the lesson is preventive maintenance even a thing for our product? And for preventive maintenance to be a thing, it needs to occur on things that wear out. If things don't wear out, there's no need to replace them. That answers the question: can we invoke preventive maintenance for this particular product? And the answer is yes. There's an observation that hazard rate seems quite linear. Someone else can hear me quite well, so I might be able to turn the subtitles off. So the changing hazard rate will tell you improving or degrading reliability over time. I understand what you're trying to say, and it's a really good observation. Just be aware that reliability will always degrade over time. I understand what you're trying to say, and I agree with you if you're talking about the nature of how reliability degrades over time. It will give you some meaningful information in that regard. So if we go back to this hazard rate curve, the most famous hazard rate curve of all is what we call the bathtub curve. And this is this curve here is all about the instantaneous likelihood that something that is working will fail now. And this is largely a conceptual curve. It's meant to describe different failure mechanisms and how they work. So we start at region 1. We have a high likelihood of failure during wear in, and we also have an increasingly high likelihood of failure during wear out. So what does wear in mean? That typically means we have manufacturing defects which are removed. So in essence, we have a subset of products which have issues when they leave the factory floor, and when you repair them, you actually take that issue away, and the whole population of things becomes more reliable. So you see the failure rate or hazard rate going down. And sometimes we can also make repairs better than new or old, which means that we might have a product that's introduced into a new environment, but we didn't realize how it was going to interact with the environment until it got there. And so not only do we fix the first failures, we replace that part with a more robust part, a part that can handle more humidity, higher temperatures, things like that. And over on this side, this typically talks about failure mechanisms where we accumulate damage. We're talking about wear out, creep, fatigue, diffusion, corrosion, all those sorts of things where you'd expect the product or system to be getting worse as it goes from day to day. I can see someone still has lost audio, so I'm just going to leave the subtitles on for the rest of the webinar just to accommodate potential bandwidth issues. All right, but this bathtub curve only applies to electromechanical systems. This bathtub curve, this purple line here, is the software bathtub curve, which again is completely philosophical or stereotypical, because it's trying to illustrate certain characteristics of failure. And in software, we often always start with a high failure rate, then bugs get removed, but then we have major upgrades. We have service packs which substantially change our software code, and we introduce a ton more bugs which take a little while to be ironed out. And if we have too many major upgrades, the overall hazard rate or failure rate will keep increasing until we reach obsolescence, particularly if we have more complex software systems. But if the software is quite simple, often we can reduce that failure rate to a very, very low figure. So you can clearly see that not all bathtub curves look like a bathtub. And here is the human bathtub curve, and you can see that that is a very uncomfortable bathtub if you do want to try and cleanse yourself in it. On the left-hand side, we have quite literally infant mortality. That's where the term comes from. On the right-hand side, you can see that's where we start to wear out. So as soon as we start having children, we start damaging ourselves on a daily basis, and parents can obviously understand exactly what that means. You can see we have a region of relatively constant hazard rate over here, where we start to enter the workforce and we aren't accumulating damage that our children impose on us on a daily basis. And you can see that on the left-hand side, perhaps over here, you can see that we have a region where there's very, very low failure rates, where we're in school, where we're protected, we're not exposed to workplace hazards, so on and so forth. So this all makes sense, and this helps us understand if we're wanting to treat the health of human beings, what we should do and where we should target our efforts. And this, you can see in this curve here, which is logarithmic on the vertical axis, this exponential increase in the hazard rate or death rate of human beings was first noticed by a man in the 1800s, and it has since become known as the Gompertz law of mortality. Now, a question was asked about servicing intervals, and can this help us understand where we should conduct servicing intervals? And part of that question was all about, I might even scroll up to make sure I get the wording correct, or the sentiment correct, where we're talking about validating manufacturer recommended service intervals versus actual life determined service intervals. Well, here is an example where I looked at the nature of failure of old vehicles in the Australian Army. This is the same example we had in our webinar regarding probability plotting, because it's such a good news story and so topical. I often include it. And you can see here, this is a hazard rate for two different populations or fleets of these vehicles, where 0 on the horizontal axis represents the servicing point. So as we go from left to right, we're looking at the hazard rate or failure rate as these vehicles keep driving after their most recent servicing action. So you can see that in this case, our hazard rate is going down as you expect. And this is because every time you touch something that was previously working, which every preventive maintenance action is, there is a finite chance of you doing something bad to it. So you see the failure or hazard rate always go up and decrease in this very consistent trend across industries. But what was happening here is, because we could understand the nature of failure, we could work out that we were servicing way too often. And these vehicles were very old at the time. They were introduced into service when we only had mineral oils, for example, not synthetic oils, which last a lot longer, but we're still servicing based on the manufacturer recommendation in a almost obsolescent technological era. And we were able to, by understanding the hazard rate, by understanding the PDF and CDF and everything else, we were able to work out that if we did less maintenance, we improved reliability by 23%. And in fact, we could have kept going the statistics bore that out, but there's a fair bit of conservative bias in the decision makers, and they only want to increase the servicing interval by a little bit, but by the same token, we increased reliability by 23%. So that's in terms of the failures we're experiencing, we dropped roughly we increased reliability by 23%, so about a quarter, which meant that we had 4/5 of the failures we previously had. So we dropped the number of failures we were experiencing by about 20%. Now, I'd argue that any industry would be only too happy to have that sort of return on investment. And the investment in this case was absolutely nothing, because all we had to do was do less servicing. In fact, we made money from doing less servicing, in addition to reaping the benefits of high reliability. So I'm just going to go back to a couple of questions here. So what do you mean constant failure rate in a bathtub curve? So that's a really good question. A hazard rate or a constant failure rate, constant hazard rate, means that your system is not getting older and not getting younger. So if the instantaneous failure probability that doesn't change, it means that your product is as likely to fail in the next hour as when you get it out of the box, as it is likely to fail in that same hour 100 years later if it's still working. So we call this the ageless characteristic of the constant hazard rate. So if things aren't failing because of wear out or maintenance issues or manufacturing defects, you see a constant hazard rate. And that typically means things like external events, like voltage spikes going through PCBs, like accidental damage, lightning strike, tornadoes, weather phenomena. You see the failures caused by those sort of external shocks as the ones that drive the failures that give us our constant hazard rate. That's what that means in our bathtub curve. Another question is, shouldn't the software upgrades create a downward trend just after implementation, not an upward trend? That's a good point. In terms of they tend to fix bugs. Yes, I agree with that, which is why we see the whole the hazard rate of our software bathtub curve going down at the start. So every time we issue a new patch, a little patch which fixes a coding error, it makes the reliability of our software improves the reliability of our software, I should say. When we have a service pack release, a major upgrade, we are introducing a ton of new functionality. It's almost like you're reissuing the software from scratch. So yes, those little patches which repair bugs, which you start seeing from day one, they make our curve go down. But when we have a major upgrade, is what we call it, we see our software hazard rate go through the roof, because we've got this bunch of new code doing new stuff, which has its own bugs, and then it starts going down thereafter. So hopefully that answers that question. The bump at 20 years is probably due to alcohol driving and overcourage. I know you're referring to the human bathtub curve, where you saw the hazard rate go from not very much to a lot at the age of 16 to 20. I agree with you, exactly. It's at least due in part to those sorts of things, but it's also due to the fact that we're exposed to more hazards, more broadly. Children going to school, it's very protected. They're not on a factory floor. They're not being exposed to, they're not driving to work. They're not on public transport. So there are a lot of, let's say, less negligent causes or reasons for the hazard rate to increase. But yes, alcohol and other sorts of things, and overconfidence in one's skills obviously starts increasing the hazard rate at that point in time. So let's see the question. By doing less preventive maintenance, reliability improved by 23%. Can you please explain how? So I'll go back to that slide in particular. So here is the hazard rate after that we determined through analysis regarding what we call the rate of occurrence of failure after servicing. So it turns out that on average, these vehicles are being serviced around about this mark here, on average about 1,000 kilometers, which for a military vehicle, that might seem like a very low figure, but for military vehicles where you're often traveling very slowly off cross country and things like that, that's not unheard of. But we were servicing right about here, so for these two fleets of vehicles. So all we had to do was push the servicing out to the right, and we started to explore this, the hazard rate as it continued to decrease, because all we were seeing were maintenance-induced failures. All these things here, we were able to demonstrate that all these failures over here, because they were decreasing, we didn't need to do a root cause analysis. We knew that they were maintenance-induced failures. These are things that were occurring because the tradesmen were making tiny errors, not negligent errors most of the time. It's just every time you touch something that was working, there's a finite chance of you doing something to it to make it not work. So because we were driving these vehicles in a way which with very trained operators, we were upgrading oils and lubricants and things like that. Our servicing interval, which used to be here, became very inappropriate. So every time we would, we would service it, we would essentially, our vehicle would travel down this hazard rate curve, get to here, and then go back to the start. What we wanted to do was ideally have our not service it until we needed to. We wanted our vehicle. Now I'm having issues with my pen. We wanted our vehicle to. It's not letting me do it now for some reason. So what we wanted to allow our vehicle to keep going down its hazard rate curve, keep going ideally until it started to go up. And only when it starts to go up do we service it and take it back here. So because our servicing interval was so short, we were constantly in this phase of maintenance-induced failure mechanisms. And as soon as we hit that 1,000-kilometre mark, we go back to the start, reservice it, reintroduce all the same failure mechanisms, and never get out of that phase, out of that stage. All we needed to do was to wait longer, wait for those maintenance-induced failure mechanisms to be worked out of the system, and then wait till we started to anticipate our wear-out failure mechanisms to kick in. So what this chart doesn't show is the back end of the bathtub curve where those wear-out failure mechanisms make our failure rate or hazard rate increase. The reason why it's not here is because we were servicing these vehicles so often, the data never got that high. So in this case, we're able to do less preventive maintenance and increase reliability. And in fact, every application where I've done this analysis, military, industrial, plant, we've shown that the manufacturer recommended servicing intervals were almost certainly increasing the probability of failure. And it makes sense because when you're manufacturing a product, you don't know how it's going to be used. You don't know how it's going to perform, even if it's used in the correct way. So you're always naturally conservative. You always want to say, let's do more preventive maintenance so these failures we hope will never happen definitely don't happen. But it's counterintuitive the effect it has on reliability. If you do it too much, you introduce too many failures. And hopefully that explains that. And again, I can't talk about it for too much longer, not in the time, but if you think that's a subject of another webinar, please let us know, and we'll also make that happen. So let's move back on to the next step. But what do we do with this knowledge we have now? What is it? We know what a PDF is, we know what a CDF is, we know what a reliability function is, the hazard rate function is. What do we do with all this stuff? What's the next step? Now we know what these things do. We know how to use our CDF curve to work out servicing intervals, work out warranty periods, so on and so forth. What is the next step? Next step is knowing which one to use. And there's, as one of our attendees suggested, there's a bunch of different options out there. Here are some examples here. We obviously don't have time to go through these today, and each one has different applications for different scenarios, and you can actually create your own. And again, that's well and truly outside of the scope of today's lesson. But hopefully, the main point from today is understanding what a PDF is, a CDF is, a reliability function, those measures of central tendency, the mean, median, and mode, how we don't want to use the mean for things like warranty, reliability, or servicing intervals, and what the hazard rate curve can tell us. And I can see one last question is, what is the unit of hazard rate? The hazard rate unit is failures per hour, or failures per year, or failures per unit usage duration. So that is that is a unit of our hazard rate. The reason why I love the hazard rate is because it's the first step for me in understanding why that thing is failing. If it's decreasing, I know we need to look at the manufacturing process. If it's increasing, we know something's wearing out. So it just automatically starts focusing us on what it is we need to do to make reliability better. So on that note, understanding that a lot of really good questions have been asked and we're right on time now. Are there any further questions? I'll be hanging around to answer them if they need to come up, but I also understand everyone has a life they need to get back to as well. But before people spear off, hey, thank you very much for attending today's webinar. We love feedback to send our reliability. If there's a topic you want us to cover, please let us know. If there's something I could have done better today, please let me know. We're always trying to improve these webinars, improve these lessons, improve the content. So please get back to us with suggestions and feedback. We really value it. And if you haven't checked out ascendreliability.com more broadly, I guess you have because you're here. But don't forget, there's a ton of other resources there as well, which includes other webinars, podcasts, books, articles, you name it. No worries. If there are any questions, I'll answer them. But thank you all for attending, and thanks for the kind words just now. Thank you for your feedback. I'm glad that you found it informative. So audience questions, how to evaluate reliability for welded joints. That obviously is a presentation in its own right. Could I suggest that you contact me directly if you want to? More than happy to discuss that further after this. There's a few things you need to concern yourself with welded joints. But yeah, please send an email to me and let's start a conversation and see if we can make to help you out. Again, thank you for your kind words. Audience question, will condition-based preventive maintenance improve reliability? How to correlate this in your slide of car example. So yes, so just to be clear, some people make a key distinction between condition-based maintenance and preventive maintenance. Now, condition-based maintenance is also preventive in terms of we're trying to stop failures from occurring, but just to get the wording right, just for the industry, we tend to use condition-based maintenance where we look for a trigger to do maintenance, and preventive maintenance where we wait for an interval to occur. But I understand what you're trying to say. So condition-based maintenance means we wait for that trigger, which means we need to know the failure mechanism, and we need to know the state of that component. So condition-based maintenance is really, really good if you do know the dominant failure mechanisms, and if you have some way to measure the rate at which the damage is accumulating on that component. So if you can, do it. But there's a couple of reasons why you can't. Firstly is cost, sensors aren't cheap. Secondly is the dominant failure mechanism might not be observable at all. You might not have might not be able to look into, be able to easily inspect a strut or something which is in the heart of the machine. So you just have to go back to intervals, which is okay. So as a rule, condition-based maintenance, where you maximize the useful life of your product, your component, your subsystem, or your system, yes, it should improve reliability. But just understand that there are some certain scenarios where it won't work or it won't be feasible or cost-effective. In the servicing for our Land Rover example, often our servicing intervals dealt with things like lubricants being changed and things like that. So we could have looked at having a sensor to look at the number of particles in oils and lubricants and work out work out thresholds, which would then invoke preventive maintenance, sorry, condition-based maintenance being triggered. And the other good thing about that is if there is some sort of premature failure in a bearing, the metal shavings will potentially give us some warning that we can change the bearing without having, before it turns into a much more catastrophic failure. So yes, hopefully that sort of answers your question. Again, if there's any other if I need to discuss that any further, please feel free to contact me directly. And yes, sorry, there's my email address there. Thank you, Fred. And again, yeah, I'd like to reiterate that thanks for attending and some really good questions, making me earn my money. Looking forward to talking soon, or talking next time, sorry.